Earlier this year, a hacker was able to compromise Microsoft's new AI-infused healthcare chatbot called Azure Health Bot. Think ChatGPT, but for healthcare. This was immediately reported to Microsoft, quickly becoming one of the highest paid bug bounties in history due to its severity. I've made a lot of videos on ChatGPT, but for healthcare chatbot called Azure Health Bot. Think ChatGPT, but for healthcare. This was immediately reported to Microsoft, quickly becoming one of the highest paid bug bounties in history due to its severity. I've made a lot of videos breaking down some of the most sophisticated cyber attacks to date. However, this one stands alone. The sheer simplicity of this exploit sets it apart, making you wonder how
I'm gonna subscribe off the bat because this is unique.
something so mind-numbingly simple could compromise a service handling the confidential and sensitive medical records of tens of millions of people worldwide. As the bot would integrate with remote data sources, this exploit made it possible for attackers to access all of the third-party data that the bot had access to, including patient databases, appointment calendars, authentication credentials, and more. What's shocking is that the bug hunter hacked Azure Health Bot twice, in two different, independent ways. What's really bizarre is that after Microsoft issued patches, they were able to exploit it a third time, and after another patch was issued, they were able to exploit it a fourth time, all functioning as standalone exploits working independently from one another. In this video, we're going to be breaking down how each of these
Yeah, we'll break it down, but I'm not trying to give anyone no opportunity to get that five-figure check. Like I work in a pharmacy, I ain't gonna say too much. I'm gonna try to figure that bug bounty out myself. I got some free time. Niggas is offering five fig. What? Alright.
four exploits function under the hood. The first vulnerability allows an attacker to trick the backend server hosting the chatbot into leaking authentication credentials and related information belonging to users on the platform. The remaining vulnerabilities are three different ways to escape the Node.js sandbox on the backend, taking complete control of the server itself, allowing the execution of arbitrary code. The implications of this are devastating, as the server is shared across multiple different users known as tenants.
You know what I just realized? We living in such a technical, literate world. Like everything is online. If you read a book, you'd probably be more ahead than a lot of niggas because books, 9 times out of 10, that motherfucker getting the information from a book he ain't fully even getting it from. Like he taking whatever bullshit knowledge he learned from a book with all the knowledge and trying to regurgitate it to his own practice. That's the internet. So, go get you a book.
It has access to all of these tenants' data. These exploits actually get progressively simpler over the course of the video, so if you get lost, be sure to stick around until the end to see where things get really bizarre. Let's begin by taking a look at the first exploit. Let's start with the fact that Azure Health Bot has a feature to be connected to remote data sources. These integrations are known as data connections. Whenever a data connection is added, the front end will send out a request to the back end in order to retrieve the data connection details and authentication information. Once received, the server will respond with the requested information. Let's take a look in more detail what one of these requests look like. There are two important things to note in this URL. This field is a unique HealthBot instance ID that is different for each user. It's not a secret, but rather a directly observable value that will be used for all requests sent to our specific HealthBot instance. In addition to this, the last number in the URL is the ID of the specific data connection we're adding. Each data connection has a unique ID associated with it. Once the server receives this request, it will do some processing behind the scenes, and then respond to the client with a JSON in this format. If you're familiar with Azure, you might have noticed that this is an Azure Table API response. If you're not, don't worry about it, as there's no need to focus on the details here, but this does give us a vital clue. This means that the server is storing the connection data in an Azure Table storage service, which is where it pulls the underlying data from. Just to recap, this means that we now know that the server is querying an Azure Table behind the scenes to get the data that was requested. Given this, the bug hunter's intuition was to start playing around with the data connection ID, as this identifies an instance of a data connection. If the
I
data
can't.
connection
I wish I could go into depth, bro, but on my mama, I'm not giving y'all no source. That is word too. Like it's right there in front of y'all. For all the hackers that already know, I hope y'all win that bounty, man. But I hope y'all leave some more, vulnerabilities for another nigga to come in and catch a check too. Cause it look like this just recycle money. You feel me? But we don't ever have to give up. Yeah, y'all know, man.
from
Y'all
multiple
know.
users are all
Come
stored in
on.
the same table, and we're somehow able to query for an arbitrary data connection ID, we would be able to access data connections of other users. Of course, we know what the client's request to the server looks like, as it is directly observable on the client. However, we cannot directly observe what the server's query to the Azure table looks like. In order to try and piece together exactly what the server is doing behind the scenes, the bug hunter took a look at the Azure Table API documentation. A generic query to retrieve data from an Azure table looks like this. Let's continue trying to reverse engineer what the server is doing behind the scenes. There are 4 values here that we must fill in. Conveniently, we don't need to look very far, as the server's response to the client discloses a lot of this. Let's sub in the values for my account, partition key, and row key, with the values returned to us from the server. Lastly, with a little bit of guesswork and
Alright, I'm not gonna be fucked up. Y'all know for this one, right? It ain't gonna be the end of video, but you can the keys and stuff as a developer, and this is just developer lessons. It's always best practice to like have the private key linked to another file, you know what I mean, rather than have the key itself posted there. And then you have that file. I don't know. I don't know. From then, I don't know what the process is like, but you would then have that file like hidden or like not something you can do where you could show the hidden files of a program. And that'll be good practice along with some security measures like let me put y'all on. I'm gonna put y'all on. I ain't gonna be fucked up. It's just sync. There you go. Snick. This what I use. I free promo done. You know what I'm saying? I ain't gonna be fucked up. I ain't gonna give you the source. I ain't gonna be fucked up. Y'all got y'all shit. You know he real because it's a Doberman that's logo. Like, come on now. You know them niggas don't beef for nobody except the niggas on their property. What more IT do you need? Alright, back to the video.
testing, we make the assumption that the table name is the HealthBot instance ID. At this point, we have a pretty good guess that this is the URL that the server is using to get the information behind the scenes. The interesting thing here is that the value being used for the row key in the server's query is the data connection ID that was originally supplied in the request from the client. This means that a value in our control is directly placed into the Azure table query. Of course, it won't be as easy as just entering an arbitrary ID in hopes that it belongs to another user, as the backend would easily deny the request. Let's take a look at how we can break this. Since our input is appended to a URL, the idea here is to leverage path traversal to cancel out the prepended information added by the server, and then add our own information afterward. Recall that the sequence ... can be used to move up a level.
Alright, I know y'all niggas got lost. I'ma draw it out for you. So, let's say this is the thing, health, and this is the server, health facility server, hacker. Alright, let me just make sure. So this basically what's going on. If you could see that little V-line thing, alright, so right here, That's the health place. Over here, that's the server. Down here is the hacker. Path traversy is intercepting the path of one of these motherfuckers, whether it's incoming or outgoing, right? And you put in the data that you want to be sent to. Well, in this sense, I'm not gonna give y'all, you feel me? I'm just letting y'all know what the shit means. But you just making sure you intercept the path and you know the information that you sending out is coming back to you. You get me? So you can talk to the machine as if you're playing that role. Yeah, that's
Level within a
about all I could
directory.
say
The
without.
way Azure treats this can be used to our advantage. Let's begin crafting our malicious URL. Rather than keeping our own data connection ID, let's go ahead and replace this with an encoded slash character, followed by 2 dots, followed by another encoded slash. When Azure goes to interpret this, it will actually end up ignoring all of the trailing characters a part of the path, effectively removing them. After this, we can go ahead and specify our own Azure query. We can place arbitrary values into the table name fields belonging to other tenants. After all of the trailing characters, when Azure goes to interpret this, it will actually end up ignoring all of the trailing characters a part of the path, effectively removing them. After this, we can go ahead with slash character, keeping our own data connection.
Hold on. Oh, that's wild. Alright, so alright, so this one is already an exploit that's been patched. This exploit basically, because we don't understand how Azure or that model really generates, it doesn't automatically take in every code that we give it. There is some code that's not like, remember the hidden thing I was saying, where you could like have your secret, how you could have your key in a file which is secret and hidden in your thing? That that is what I'm talking about. Like that key, that request is kind of like the full request, but there's like a secret key that it doesn't always, no, it doesn't read that bitch at all, but it still intakes it and holds it in. So whatever information passed through there, in theory, which is why that hack is devious, in theory, you should be able to reprogram whatever is going on within that request.
ID, let's go ahead and replace this with an encoded slash character, followed by 2 dots, followed by another encoded slash. When Azure goes to interpret this, it will actually end up ignoring all of the trailing characters a part of the path, effectively removing them. After this, we can go ahead and specify our own Azure query. We can place arbitrary values into the table name fields belonging to other tenants. We can also place arbitrary data connection IDs into the row key fields belonging to the data connections of other tenants as well. This way, with some trial and error, we can actually get our hands on the data from other tenants within the Azure table. Notably, we need to leave out the final quote, as the server-side URL that this is getting placed into still has its own trailing quote, and we don't want to invalidate the query. All we need to
Mm-hmm.
do now is send off this attacker-crafted request, and the server will successfully return the data connection details and authentication information of other users. If you think that tricking the server into leaking information is bad, now we're going to turn to the remaining 3 exploits, each of which are different ways to escape the Node.js sandbox on the backend, taking control of the server itself. The intent is to be able to
That I gotta, it's not that I don't know what, like they say sandbox a lot. The sandbox is a testing environment that isolates untested code changes. Okay, let's sandbox. A sandbox is a testing environment. Okay. Sandbox serves as a development testing environment, enabling organizations to run applications. All right. Sandbox. But what is a sandbox's purpose? Hard code it to make a user stay in sandbox, but you can also get hacked if a person knows how to break out the sandbox. No. So a sandbox main purpose is to isolate, create a controlled environment where code programs can run without affecting the rest of the system. Oh, testing developers can potentially test and developers can safely test and potentially risk code security. It contains malicious software. You make a valid point about a sandbox. No security measures is perfect, and they're exploiting buffers and a sandbox is valuable for defense step strategies. I cool. Wait, you saying a sandbox is not really open? It is the pre app before. Wait, it is the simulation. There we go. Simulation uh, before or while the app is pushed to production. So every app have a sandbox that it communicates to in real time for update or measures that affect the app. Let me clarify. Sandbox really isn't a simulation or real-time features. You think of it more like a contained workspace or a sealed box. When developers or users and Sandbox is running, it is running the actual app, but with strict boundaries around what it can access. Oh, you install the mobile app. So the sandbox is a completed app, but completed app is pushed to production. So in a sandbox, you can do everything you need in a controlled environment that allows you to either test on false or imaginary data or push to production with access. I know I get what you're trying to understand. Yes, you got a good grasp on Bill. Won't you say something is basically a safe playground? Okay. Dummy data. When an app is live, but still need boundaries, real data, but with controlled access. So you're right. It's not that a sandbox is necessary before production or in production. It's a security concept that can be used in both the scenarios. Think of it like a fancy restaurant. You have a kitchen, you have a test kitchen and the actual kitchen. Development, sandbox, and production. Okay. Low key.
Execute shell commands in order to try and find a way to access data from other tenants. It turns out that Azure Health Bot has a feature that lets you execute your own JavaScript code in an isolated, sandboxed environment on their own backend. The bug hunter began to do a little reconnaissance within this sandbox and realized that they were running inside of a VM2 sandbox, which is a popular Node.js sandboxing library which, as they stated, has since been discontinued due to multiple unrelated security flaws. Normally, in Node.js, you can execute shell commands by importing the child process module and using the exec_sync, or spawn methods. Of course, it isn't going to be this easy, as we are running inside of a restrictive, sandboxed environment. Microsoft implemented a custom require function, which only lets you import a tiny selection of pre-selected, whitelisted modules chosen by Microsoft. Conveniently, JavaScript actually lets you view the source code of any function, simply by calling the .toString method. If we call toString on the custom require function itself, we can view its source code. As we can see here, a quick binary search is done against the whitelist, and only if the requested package is found in the whitelist does it go on to make a call to the original require function. If the requested module is not found in the whitelist, an error is thrown instead. While this may look harmless at first glance, you might have noticed that they are using the _.indexOf function rather than the native JavaScript array indexOf method. This is actually quite interesting. The _.indexOf function that they are using is the function from the underscore module and is not a native JavaScript method. This enables us to do something interesting. Why not simply override the indexOf function? We can easily access this function within the underscore module and assign a newly defined function in place of the existing implementation. In the bug hunter's proof of concept, they simply defined a function that returns the integer 10. Let's see how damaging this can actually be. Turning back to the start, let's see what would happen if we now try to import the child process module to execute shell commands. When the custom require function receives child process as the package name, it will check if it's a whitelisted module. Of course, we know that _.indexOf is now going to return the integer 10, which will always be greater than 0. This means that this entire segment will always evaluate to false, resulting in the entire if statement evaluating to false, skipping over the error condition entirely, leading to importing the requested module without actually checking if it's whitelisted. Once the child process module is successfully imported, we're free to execute whatever shell commands we want on the server. At this point, we're actually running as root inside of the server, which of course has access to the Azure table containing data shared between all of the different tenants. Within 24 hours of being reported, Microsoft patched this. After this patch was issued, the bug hunter was able to find another way to execute shell commands on the server. This time, they focused on trying to abuse a whitelisted module itself, rather than trying to bypass the whitelist enforcement mechanism altogether.
Wix. Yeah, you know what's crazy? It's hard to really fight against it because how can
Whitelisted
I, you know how they tell you if you being followed by the police, you just got to drive straight because sometimes you could get pulled over, or you might as well pull over in a gas station because you can get pulled over for anything. There's probable cause police is looking for, not a fucking reason to pull you over. Like you could get pulled over for nigga think your light's not on. So this the same shit. You in a sandbox, you could get hacked in any way, shape, or form. It don't matter if you patch it, your patch could get hacked. You could get hacked. The system could get hacked. Like there's so much open points in that sandbox.
module would actually be quite helpful, as the whitelisted modules run outside of the VM2 sandbox, directly in the root Node.js context. Coincidentally, they found something of note within the underscore module yet again. Within underscore.js, there's a function called template. The premise of this function is quite simple. You just hand it an HTML template in string form, and it returns a function that can be used to dynamically sub values into said template. The function can both interpolate values using the angle bracket %= sequence, as well as executing arbitrary JavaScript code with the angle bracket % sequence. This means that you can hand the template function arbitrary JavaScript code, and it will happily execute it. Of course, this execution happens outside of the VM2 sandbox, as it is the module that executes it, not us directly. The reason why this happens is a little bit technical, but in short, when a module is passed down from the root context to the sandbox, it retains all of its original root context permissions. Knowing this, from within the sandbox, we can simply call the template function and place some JavaScript within the applicable sequence. We can hand it similar code to what was used in exploit 2, which will successfully import the child process module, since this code will end up running in the root context. Once again, we've achieved the ability to execute shell commands on the server. After being reported, Microsoft was quick to issue another patch. Turning to the fourth and final exploit, we're going to leave all of the whitelisted modules behind and focus on a native, built-in Node.js module called buffer. In the case that someone wants to allocate a memory buffer, they can use the buffer.alloc method. This will return a memory buffer that is zeroed out. This just means that the data contained within the buffer is set to all zeros. Another method exists that also returns a memory buffer called buffer.alloc_unsafe. This method is faster than using alloc since it will not zero out the buffer. Instead, it will simply return a chunk of memory as is. If sensitive data previously resided in the same memory location that alloc_unsafe returns, you would be able to read the data that was left behind. If we repeatedly called buffer_unsafe within the sandbox, we could essentially fish for sensitive data left behind from the root context. Of course, it's not going to be this easy. The VM2 sandbox purposefully restricts the use of alloc_unsafe for this exact reason. Let's see where things go wrong. Rather than explicitly allowing the use of buffer.alloc, they explicitly restrict the use of buffer.alloc_unsafe. All of the other methods a part of the buffer module are still allowed to be used. Interestingly, there's a method that is nearly identical to buffer.alloc_unsafe called buffer.slowBuffer. It is an old, deprecated method that was unintentionally left in. Many years ago, the newer alloc_unsafe method was intended to replace slowBuffer.
And that's another thing. Some of these businesses are using NPM, and NPM is the only JavaScript library. And it's not just JavaScript, it's Node.js, 3D.js, Cornerstone.js. You know how much motherfucking JSs there are out there? I ain't gonna cap. I don't got time to be laying it down. Just know there's one library, just one. So anything that's like from the 2000s and shit, that shit's still there, bro. If your company is using some shit that's just not like updated with the dependencies, hey, look, man, you are at liable risk of a hack like this anytime.
As Node.js evolved and its memory handling capabilities became more optimized. Turning back to the exploit, since we are allowed to use slowBuffer, which returns non-zeroed memory, we can start fishing for chunks of memory that could contain sensitive information. With some trial and error, the bug hunter was able to access a few JWT secrets for internal Azure identities, Kubernetes API calls, cross-tenant data, and more. After the fourth exploit was submitted to Microsoft, they rolled out multiple, dramatic security changes. As the bug hunter noted, they changed the service architecture to run a completely separate Azure container instance per customer, making any potential future sandbox breaches irrelevant. They also changed the sandboxing library from VM2 to isolated VM. It's not uncommon for some of these vulnerabilities to end up hiding in plain sight for years before a bug hunter is able to spot them. Being able to spot these
Yeah, you know how lazy a programmer is, bro?
vulnerabilities often requires a mix of effective problem-solving skills, pattern recognition abilities, and a strong foundation of key mechanical concepts. Luckily for you, it's easy to stay on top of this thanks to this video's sponsor, Brilliant. gives you hands-on experience. Daniel Bochter or 20%. If you're interested in more vulnerable.
All right, that was a video. But nah, I like that because when it comes to hacking and just the whole idea of the white hat, black hat, I honestly feel like just that niche, the IT and all of that, them just people who just did uh, a different type of programming. Like front end development is no different from a nigga injecting some shit in your HTML. You still got to figure out what the fuck going on.